Go is fascinating. I agree. All right, we're right on 3 o'clock, so I'm going to go ahead and get started. Before I dive into, um, don't hear the plane. That's great to hear. Um, before I dive into the topic for today, just a little bit of housekeeping, business, whatever. Now the airplane sounds loud to me. If you hear it, let me know. I'm going to ignore it otherwise. This is my first time streaming on LinkedIn. So I've done this. This is my 6th time, I think, to YouTube. I decided to install Restream.io to multi-stream to both YouTube and LinkedIn. So I see a good number of people coming from both platforms. That's really good. But if there's any problems, let me know. Those problems could be audio, video, lag, if the resolution's bad, anything like that. If you discover anything wrong with the live stream today, let me know, and I'll try to improve it for next time. Okay, I just got a comment that it feels like you can't see the chat. So the reason for that is almost certainly because those of you on YouTube can only see the YouTube chat, and those of you on LinkedIn can only see the LinkedIn chat. I can see both. So if you see me referring to a comment that you don't see in chat, that's why. So that might be a little bit weird, but that's what's going on. So I apologize for that. I don't know of any solution to that. I don't think there's any bridge between LinkedIn and YouTube chat other than my voice. So hope that makes sense. If you're new to this, and I think those of you on LinkedIn probably are, I'm glad you're here. I've been enjoying doing live streaming. I hope that you find something valuable today. I'd also like to invite you to my my YouTube channel if you're coming from LinkedIn, or to my LinkedIn if you're coming from YouTube. I love to get followers both places. And I also want to mention my daily email. I write a short email every day, 5 days a week, about Go. Right now I'm going through the Go spec. I'm about halfway through. I've been doing this since January, so I guess it's about a year-long project. Most days I'm taking a small chunk of the Go spec and explaining it in more simple terms, at least when possible. Sometimes it confuses me, and I'm learning too. But you're welcome to join. That's at boldlygo.tech/daily. You can sign up for that if that sounds interesting. And if not, that's perfectly all right too. Yeah, Shelby suggests if you want to see the chat on both, you can log in to both LinkedIn and YouTube and eat a ton of RAM to watch me twice. Probably mute one of the tabs so you don't hear the reverb or whatever. Anyway, today I am going to learn how to do fuzzing in Go, or fuzz testing. I've never done this before. It's a feature that was added to the Go standard library back in version 1.18, which was February last year, I believe. And I've been excited to try it. I just never have. You can see on the screen I'm sharing here, there's this blog series, 4-part series, started back in April, written by John Arundel, who I recently interviewed with my co-host on the Cup of Go podcast. So if you're interested in Go, there's a podcast I'm on too. You can listen to at cupofgo.dev. But he has this 4-part series about fuzz testing, and I've skimmed it because I talked about it on the Cup of Go podcast, but I haven't read it in depth, and I haven't read every post. I'm going to do that today. I'm going to read it out loud to you, and we're going to do some live reading and live coding. I don't know how much coding there is in the first section. There's some code, but we'll see. I'm learning as we go along here, so we're all learning together. So I'm just going to dive in. I'm going to read it, and I guess it's kind of a hybrid reaction video slash live coding slash learning together, whatever. So let's start. The first one. And I guess I should share the link. I'm not sure the best way to do that. I think I can put it in the chat here. So if anybody wants to follow along, I can't post messages to some channels. I don't know if my chat goes to LinkedIn. I'm going to log into both and eat RAM so I can share my chat to LinkedIn. So I can chat to LinkedIn too. It says fails to post comment. I wonder why that is. Well, I don't have any idea what's going on there. I think I'll have to fix that later. Hi, Jason. Yes, you caught the beginning. I'm just going through some housekeeping stuff and intro. Anyway, I don't know why I can't share the link. I'm trying to chat on my own LinkedIn and it's giving me an error. Failed to post comment. Well, if you really need it, send me a DM and I'll send you the link. I'll try to figure that out for next time. So I'm going to start. Here we go. This is the first of a 4-part tutorial series on fuzz testing in Go, or on fuzzing in Go. I added the word testing. Part 1, where we are, random testing in Go. Then we have fuzz tests in Go, writing a Go fuzz target, and finding bugs with fuzzing. Choosing a good test case for our Go programs can be a bit hit and miss. Sometimes we get lucky and find an input that causes incorrect behavior or even a crash. But in general, picking inputs at random isn't a good way to find bugs. I agree with that. If it's not clear, the context here is you have some unit tests, or you're writing unit tests for your Go code. What are you going to test for to try to validate that it works? Say you have a Fibonacci calculator, and you want to get the 4th value or the 12th value, whatever. Which values do you choose, and how do you verify that they're useful ones? Or is it? So he just says random isn't a good way, or is it? What if we leaned into an idea a little and we used a lot of different inputs, say 1 million or even 1 billion? With that many inputs, our chances of finding one weird value that triggers a problem start to look pretty good. Sound like too much typing? I agree with you. So let's get the computer to do the work instead. Isn't that what they're for after all? Generating random test inputs. Well, we know how to generate random numbers in Go. We can use the mathrand package for a more cosmic level of randomness, bitfield qrand. I don't know what that. I'm curious about that. Cosmic. What is cosmic randomness? Quantum mechanical process. Okay, that's awesome. I don't know. I'll look at that later. There's also the cryptorand package if you need something that's actually cryptographically secure. That's part of the standard library. Suppose we have a pair of functions, encode and decode. It doesn't matter what they do exactly, but we can assume that if you encode something, then decode the result, you should get back what you started with. If the functions are working correctly, that is. Here's a test that generates a random integer between 0 and 9 and sends it on a round trip through 2 functions, encode and decode. Thanks, Jason, for sharing that link. All right, so here's some code. It imports mathrand, and it has this big, huge, long function name, func test encode followed by decode gives starting value. Okay, at least it's descriptive. We call t.parallel to run the test in parallel. Our input is some random value between 0 and 10. Oh, maybe it's 1 and 10. I think it's 0 and 10. I don't know if I don't know how that function works, or if the description is wrong, because it says 0 and 9 here, and then I think this actually returns between 0 and 10. Anyway, doesn't really matter. Encoded equals codec.encode input, so we encode the input. We log the encoded value as a sort of Go native representation of it. Then we want the result to be the same as the input. I guess we're just assigning it to a new variable for clarity's sake. Then we call decode on the encoded value, assign that to got, and then we check if want equals got. If it doesn't, we print this output. We want %d, but we got %d. Simple enough. You might worry that if the value is truly random, then we could end up with a flaky test. If there's a bug in encode or decode that's only triggered by certain inputs, then won't a test like this sometimes pass and sometimes fail? That's definitely a possibility. One way to avoid that is to seed the random number generator with some fixed value. That way the generated sequence will always be the same, making our test deterministic. For example, we could write something like this, which will create a new random generator just for the tests, seed it with value 1. Yeah, okay. We don't have to use 1 as the seed. Any fixed seed value will do. The point is that given a certain seed, calling rng.int_in will always produce the same sequence of values. So here we go, 1, 7, 7, 9, 1, etc. If we did happen to want a different sequence every time we run the test, we could instead use some seed that isn't fixed. For example, the current wall clock time. Yep. By the way, just as a side note, unrelated to this particular tutorial, if you're doing this and you think it's secure, think again. If you need secure random numbers, use crypto rand instead of math rand. There are ways, depending on how your application's built, that a potential attacker might be able to predict the time or even control the time that the RNG is initialized. Randomly permuting? I wanted to say permutating, but I don't think that's a word. Randomly permuting? I don't know where the emphasis goes there. Anyway, randomly permuting a set of known inputs. A nice way to use randomness without causing flaky tests or having to manually seed a random generator is to permute a set of inputs, that is, rearrange them in some random order. For example, the following code generates a slice containing the integers from 0 to 99, ordered randomly. Okay. I wasn't familiar with this rand.perm, but that's cool. So I guess it takes, well, I'm going to look at the Go doc for that because I'm really curious. Perm returns as a slice of n ints, a pseudo-random permutation of the integers in the half open interval, 0 to n, from the default source. Okay, yeah, so you pass it a number, 100 in the example, and it creates a series of numbers from 0 to 100 in randomized order. That's kind of cool. I didn't know that existed. The sequence of 100 integers generated by rand.perm 100 is not random itself, since each value from 0 to 99 will be represented exactly once. That wouldn't be true of randomly chosen numbers, where some values would occur multiple times and others not at all. Instead, the sequence is randomly permuted, that is, randomly ordered. It's like shuffling a deck of cards. You know that each card will show up exactly once, you just don't know when. Just like rand.int_n, the result will be different for every test run unless you create your own random generator initialized with a known seed. Property-based testing. Randomness can be a good way of finding interesting new test cases that you might not come up with by yourself. For example, if your function takes integers, you might have tried testing it with 1, 5, 7, and so on. You might not have thought of trying 0 as an input, but the random generator would likely produce that at some point. And if your function breaks when given 0, then that's something you certainly want to know. So that kind of goes back to the example I made up at the beginning with a Fibonacci calculator. If that's what you're testing, you wouldn't know. I mean, there's an infinite number of inputs you could give it. Which ones do you try? Maybe you try some random ones and see if anything breaks. Good testers in general are good at suggesting inputs that break the program because the programmer didn't think of them. Randomness can help with that process. One problem with randomized test inputs that may already have occurred to you is this. If we don't know in advance what input we're going to use, we can't know what answer to expect as the result. That certainly would be true with my Fibonacci example. I mean, unless you've calculated it ahead of time, but assuming you haven't. Test squared gives correct result. T.parallel to column parallel again, then we give it a random number between 0 and 100, and we square it. Yeah, if we get 13, what's the square of 13? Unless you know already, you have calculated it, you don't know what to test for. So what's our want value here? We don't know because we don't know what the value of input will be when the test runs, and thus what its square would be. If we knew that input would be 10, for example, then we could have the test expect the answer 100, but we don't know that. We're stuck. Now, we don't want to try to compute the expected result in the test because clearly we could get the computation wrong. In the most pernicious case, we might end up using the same code path to compute it in the test that we use in the system, so we end up testing nothing at all. So, yeah, I mean, he makes a really good point here. There are times when I will have a test calculate the result I expect the result to do, but only if it makes sense to do that using a different approach that's maybe simpler or something like that. It's rare that I would ever do that, but I have done it a few times. I can't think of a specific example right now. But certainly you don't want to test your code using this same code that you're testing, because like he just says, it doesn't test anything. If we can't predict the exact value of square, if we can't predict what the exact value of square will be for a given input, is there anything we can say about it in general terms? Actually, there is something we can say. It couldn't be negative, that's true. No matter what the input, if square returns a negative result, something's gone wrong. So although we can't predict the exact result, if the system is incorrect, we can still identify some properties it would have. So we could write a test that calls square with lots of different inputs and checks that the result is never negative. All right. So we range over 100 values, and we check if the value is less than 0, then we have an error. This approach is sometimes called property-based testing to distinguish it from what we've been doing up to now, which we might call example-based testing. Another way to think about it is that property-based tests describe the behavior of the system, not in terms of exact values, but in terms of invariance, things that don't change about the result, no matter what the input is. In the case of square, for example, its result should invariably be positive. Randomized property-based testing helps to fix the problem that maybe the function only works for the specific examples we thought of. And although we generate the inputs randomly, once we find some value that triggers a bug, it should then simply become part of our conventional example-based test. So if we discover that square fails on an input of 13, then maybe we want to add an example-based test that checks 13 against the known result, the known correct result. All right, we could do this by manually adding such values to the sets of inputs in a table test, for example, but there's no need. Go provides an automated way to turn randomly generated breaking inputs into static tests for us, using what's called Fuzz testing. In part 2 of this series, we'll introduce Go Fuzz tests and see how they can be used to find rare inputs that trigger bugs. Stay tuned. Well, this is the nice thing about waiting until the series is done. You can binge watch. All right, this is the second of 4 tutorials. Nobody's perfect, especially programmers, and while we try to be reasonably careful when writing code, we're bound to overlook things from time to time. Bugs often arise when the programmer doesn't envision certain kinds of inputs, and thus doesn't test that the system handles them correctly. In other words, you can find bugs. In other words, you can only find bugs you can think of. I guess it's more or less true, yeah. Slice overruns are a classic Slice overruns are a classic example of the kind of bug that busy programmers can easily overlook. Oh yeah, I have overlooked these myself many times. Yep. So here we call search products on an ID, and we get a result or a list of results, and then we check the name of the first one. But if there are 0 results, then that panics. Indeed, this code might run perfectly well in production for months or even years, and then suddenly break when someone searches for a product that doesn't exist. It wasn't caught by any example-based tests because nobody thought about the situation. I've seen that many times. But there's another kind of testing that can help, fuzz testing. The fuzz here refers not to data that's blurry or imprecise. What? That's what I wanted. But means simply randomly generated. We saw in part 1 that it's possible and useful to generate random test inputs in plain old Go code, but it's nice to have an automated way of doing it too. Tools for fuzz testing have been around for decades, but built-in support for it was added in Go relatively recently in version 1.18. As I mentioned at the beginning, I think that was released in February last year, so it's a year and a half it's been around. Same time generics were added to Go. Could we boost our chances of finding lurking bugs in a Go function by fuzzing it? That is, by randomly generating lots of different inputs and seeing what happens. To find out, let's deliberately write a function that will panic when given a certain secret trigger value. All right, so this one will panic if it gets input value of 21. Now we'll pretend we don't know the special value, but we merely suspect that such a bug lurks within the function. We'll try to find it using randomized inputs. How could we do that? We need to generate a large number of random values that decently cover the space of likely inputs and call the function with each of them in turn. If one of them causes a panic, then we have found our bug. It's not that we couldn't write this by hand, it's as in the previous examples, but instead let's try writing a fuzz test using Go's standard testing package. Here's what it looks like. One quick note, there have been fuzz tests in Go for a long time. I haven't used them either, but before they were in the standard library, I know there was at least one third party and probably more than one third party tool for fuzz testing in Go. And there may still be reasons to use those. Maybe they have some features that the standard library doesn't have. I don't know. But now they're in the standard library. So that's the whole point of this series. All right, fuzz guess. We call f.fuzz with the function, and we give it an input. Okay, so the fuzz library presumably is generating an input and passing it into this function, and this function passes it to guess. I'm sure it's going to explain that, but that's what it looks like is happening. So we don't have to worry about this. Presumably, it's smart enough to detect, to recognize the input type and then start passing integers of, values of integer type rather than some other arbitrary type. I'm guessing also there must be some way to specify ranges. Like if we know that anything over 100 is always invalid, we don't need it to be passing in 16 million. So I imagine there's some way, we'll learn, I hope, to tell it what range of values are useful to test. The names of fuzz tests in Go start with the word fuzz, just as a regular test starts with the word test. And the parameter they take is star testing.f, which is similar to our friendly star testing.t, and has many of the same methods. The fuzz target. What do we do with this f parameter then? We call its fuzz method, passing in a certain function. Passing functions to functions is very Go-like, and though it can be confusing when you're new to the idea, it's also very powerful once you grasp it. So what's this function within a function? In fact, it's the function that the fuzz testing machinery, the fuzzer for short, will repeatedly call with different values it generates. We call this function the fuzz target, and here's the signature. That's the one I was just looking at. Remember, this isn't the test function. It's the function we pass to f.fuzz. And although it must take a testing.t as its first argument, it can also take any number of other arguments. In this example, it takes a single int argument that we'll call input. These extra arguments to the fuzz target represent your inputs, which the fuzzer is going to randomly generate. In other words, the fuzzer's job is to call this function, the fuzz target, with lots of different values for input and see what happens. And here's the fuzz target we'll be using in this example. So it seems like my guess was pretty much spot on, that this is random, that it looks at the type and randomly generates values of that type. This very simple fuzz target does nothing but call guess with the generated input. We could do more here. Indeed, we could do anything that a regular test can do with the t parameter. But to keep things simple for now, we just call the function under test without actually checking anything about the result. So the only way the fuzz target can fail is if the function either panics or takes so long to return that the test times out. All right. Running tests in fuzzing mode. To start fuzzing, we use the go test command and add the -fuzz flag. I feel like it might be time to write some code here and test this thing out, huh? I have, where's my window? I have a window open somewhere. There it is. Let's go mod init get lab.com/go fuzz. I probably won't push this code up publicly. When I'm live coding, I usually like to make my repos publicly available. But since I'm just going to be, as far as I know, copying and pasting code from a tutorial that's already online, I probably won't push this one anywhere. But just in case, I give it a valid module name. All right. So where is that code? This code right here. Let's copy this, and then I need to copy that guess packet or function also right here. Now he's calling guess in a separate package. I'm going to cheat and do it in the same package. just because I'm lazy. All right, where were we? Here. So I have this. No, actually, I need to move this fuzz to fuzz test. It's going to be in a test. It's going to be run by the code test tool. Whoops, I should put two Z's in the word fuzz. Right, I think it's doing something. I don't know how long this is supposed to run. Note the dot after fuzz, which is significant. Did I put that there? Yeah, okay. I did. Just as the dash run flag takes a regular expression to specify which tests to run, the dash fuzz flag does the same. In this case, we're just using regular expression dot. Okay, yeah, that makes sense. So we have to tell it what fuzz test to run, and dot means essentially run all the fuzz tests, of which there are only one in this example. And here's the result. Yeah, that looks similar to my result. Wait, it's not exactly the same. Because I'm using Go 1.20 now. Maybe it's changed. But I have two lines here. The first one says 0 seconds, execs 0, 0, blah, blah, blah. All zeros, just like he has. And the second one is different. And it says 413 execs. And I found an interesting one. I don't know. Hopefully it makes sense soon. I mean, I think I understand what happened. It found the panic, but I don't know why the output's different. The first thing to note about this output is that the test failed. Specifically, it failed with this panic. So his also failed too, the same way mine did. I just had this extra line of output for some reason. Whatever. This is the panic message that we deliberately hid inside the guess function. It didn't take long for the fuzzer to find the secret input that triggers the panic. But what was it? Sometimes I have such hard time reading simple words. This isn't shown as part of the input, but here's a clue. Failing input written to. Okay. Do I have the same thing? Yes, I do. Instead of XXX, the actual file name is some long hexadecimal string. Yes, indeed it is. That I won't weary you by replacing in full. We don't normally need to look at the content of these files, but just for fun, let's take a peek. All right, let's take a peek. Mine also. I bet it's the same. Go test fuzz v1 int 21. Yep, looks the same. The first line identifies what kind of file this is. It's generated by v1 of the Go fuzzer, including a version identifier, like this is a good idea when generating any kind of machine-readable file. By the way, yeah, I agree. If you decide you'd like to change the file format later, you can alter the version number to maintain compatibility with older versions of the reading program. The second line contains the information we're really interested in, int 21. This gives us the specific input value represented by the test case. It's an int, which is no surprise since that's what our fuzz target takes. Yeah, that's exactly what we thought. Winner, winner, chicken dinner. It's got to be a link to a movie. No, it's a link to a blackjack game, apparently written in Go. All right, let's keep going. Why has the fuzzer generated test data file then? Why not just report the failing input as part of the test results, for example? I have some guesses about why it did that. Well, suppose we grew bored of fuzzing for the time being and we decided to just run our plain old test again without the -fuzz flag. Yeah, I'm bored. I'm going to do that. Hey, how did that happen? I never wrote a test to do that. Why is it running a fuzz test if I didn't say fuzz? The answer, as you may have guessed, is that fuzz tests can also act as regular tests. When run in non-fuzzing mode, that is without the -fuzz flag, they don't generate any random inputs. What they do instead is call the fuzz target with any and all inputs that have previously been found to trigger a failure. These are the inputs stored in the special folder test data. Yeah, that's kind of what I was guessing. And that's pretty cool. I didn't know it did that. That's pretty sweet. As it happens, there's only one such input at the moment, 21, but it's enough to fail the test. A good way to think about the fuzzer is that its job is to generate failing test cases, which then become part of your normal example-based tests. In other words, once some randomly generated failing input has been found by the fuzzer, running go test will test your function with that input ever afterwards. Unless you choose to remove the test data file manually, of course. Let's fix the function so that it no longer panics on 21, or indeed does anything at all. All right, so we're going to an extra window open here. We're going to, do I have an extra window open here? What happened? I must have closed too many things. Oh, one moment. Oh, I know what happened. I moved that file, and then that my editor was like, oh, that file's gone. All right. So we're going to remove this here. Now it's an empty function. And I'm jumping ahead of the tutorial, but if I run go test, it should pass now. Indeed it does. Let's use go test with the -v flag. All right. To show that the 21st test case now passes. Yep. I get the same thing. I wonder if this, just out of curiosity, I wonder if this hexadecimal number is some sort of hash or if it's random. I'm going to find out. You know how I'm going to find out? I'm going to delete it. Let me undo this. Now I'm going to copy and paste this into my editor just to remember it for the moment. All right, so there's our what our failing test looks like, or is called right now. Let's delete test data and do this again. Go test minus fuzz. Whoops, still need an extra z there. And it gave me the same number. So it's some sort of hash. That's awesome. That's actually really cool, because that means that if I'm running fuzz tests on my local machine and you're doing it on your local machine, we're not going to end up with, and we both find the same failure and try to commit them to Git, for example, we're not going to end up with duplicates with different names. So that's really cool. I like that. It also means if I accidentally delete my thing here, I can get it back again, or I can know if I get it back by comparing file names if I got the same failure again. That's really cool. Toy Story 4. What's the reference there? I probably just breezed right past it and it probably was good timing, and I'm just way late for the joke, but all right. I think we're almost done here. This is a neat feature. That means the fuzzer automatically creates regression tests for us if we should ever write a bug in the future. Every time a new failing test case is found by the fuzzer, it becomes part of the regular test suite. Yep, that's cool. In part 3, we'll see how to write a more sophisticated fuzz target. Also, cake will be served. Oh, I can't wait for the cake. If there's no cake, I'm going to be upset. All right, writing a Go fuzz target. In part 1, we talked about generating test inputs randomly. Yes, we did. In part 2, we saw how Go's built-in fuzz testing facility can automate this process. Yes, we did. Let's take a more complicated and realistic function now and try to use the fuzzer to surface one particular kind of bug that's fairly common in Go programs: accidentally mixing up bytes with runes. All right. I'm not sure how much detail it's going to go into here. I guess it looks like it's going to. So I'll hold off my critique or my commentary to see how detailed the explanation is here before I offer my own explanation of runes. First, to set the scene, a word or two about strings. I need to slow down my talking. First, to set the scene, a word or two about strings, bytes, runes, and characters in Go. I must have a blog post about this. Looks like it, yeah. As you may know, Go has a thing called runes, which represent individual characters of text, such as X or exclamation point. You probably also know that a Go rune can represent not merely the 256 possible single byte characters specified by ASCII, but also the full set of 150,000 odd Unicode characters, including... Can anybody pronounce those? I can't. I don't even know what language those are all in. Okay. This means that your Go program can deal with the alphabets of just about every human language and many other characters besides, such as emojis and Klingon and other non-human languages, as far as I know. Okay, this does mean, though, that it can take more than one byte to represent a Go rune. Since a single byte only gives 256 possible values, I read that with wrong inflection, but you get the point. So it's not safe to write Go code that assumes each byte of a string represents a single character. Such code will produce the wrong result when given a non-ASCII input, such as accented letters or Chinese characters. Suppose we want to write a function first rune that takes a string and returns its first rune. Given the string hello, let's say it should return the rune H. That sounds doable, doesn't it? I can't really increase my mic volume very much. I'm already almost redlining. I think I need to investigate why, because I've had this comment a couple times that I'm quiet. I don't know if the software is down, reducing the volume a little bit, reducing the gain. I don't know what's happening, but my mic is already almost redlining, so I can't really go up any higher without problems. So I guess you'll just have to increase the volume on your side. I'm speaking as close to the microphone as I can for that purpose too. All right. In a programming language where there's a one-to-one correspondence between runes and bytes, this would be straightforward. If the string is S, for example, we could just simply index the first byte of the string, S0, and be done, and return it. But that won't work in Go because the byte may be merely the first part of a multi-byte UTF-8 sequence. Indeed, it can take up to 4 bytes to represent some Unicode characters. We just won't know what we've got until we look at the actual bytes. Let's see if we can use fuzz testing to catch this kind of error then. We'll use a fuzzer to generate random inputs and see if any of them produce the wrong answer from first rune. Here's an example of such a test. All right, so we call f.add hello and f.add world. I'm guessing that's like adding our own inputs, I guess, since we know we're getting a string here. So we're sure to test those cases, I guess. I'm sure it will explain, but that's what I'm guessing this means. Then we call our function runes, our first rune, assign the return value to the got variable. And then we call this function in the standard library to decode rune in string to get the first I guess it returns the first one. I'm not sure. Let me see what that does. It's called decode rune in string. Let's see what that does. Decode rune in string is like decode rune, but its input is a string. If S is empty, it returns rune error. Otherwise, if the encoding is invalid, it returns rune error 1. Both are impossible results for correct and non-empty UTF-8. And encoding is invalid if it is. All right, so what I care about here is what decode rune does then. It says it's like that. Decode rune unpacks the first UTF-8 encoding in P and returns the rune and its width in bytes. Okay, so basically this function does exactly the same thing the function we're testing should do, first rune, except that first rune doesn't return the width in bytes. But that's fine. If want equals rune error, then we skip. So what that means, so that as we were just reading, this can return this rune error if it's an invalid UTF-8 character, in which case we don't want to do this test because we apparently don't care about it, so we just skip it at that point. Otherwise, we continue along. If want and got are different, then we produce this error. 2 errors, actually. One showing what we want and one showing what we got. Okay. It might look a little alarming at first, but we'll break it down line by line. The general idea is to call first rune with some string randomly generated by the fuzzer and compare the result against what the oracle, in this case the standard UTF-8 decode rune in string function, says it should be. If our first rune function works correctly, it should give the same rune result as decode rune instruct for all inputs. But if there's a bug in the function, its result won't match the oracle. Yep, makes sense. And fuzz target will mark this as a failing test case. Makes sense to me. While, as we've seen, the fuzzer is quite capable of generating random values from scratch, it can be helpful to give it some starting inputs as hints. Remember the mysterious warning it gave us when we ran the fuzz test for guess function? Warning starting with empty corpus. The fuzzer's corpus is the set of training data that we give it, if you like. It can still fuzz even with an empty corpus, as we saw, but it helps if we provide a few example values for it to start with. These will be supplied to our fuzz target and tested. The fuzzer will then generate more inputs from them by mutating them randomly. Oh, okay. So that's why this add is called. It's not just seeding it with two examples. It uses those examples to mutate and come up with other randomized variations. We call f.add to add more example values as many times as we like. The more training data we give the fuzzer to suggest possible lines of attack, the better. The corpus also includes any previously generated failing test cases stored in the test data fuzz folder, like the 21 in our previous example. So over time, we'll build up bigger and bigger corpus, which gives the fuzzer more to work with. A more sophisticated fuzz target. Next comes the call to f.fuzz with our fuzz target. Is this not what we just saw? Just simplified with the failure omitted, I guess. First, we'll call the function and save its result to the variable got. I guess we're just walking through it, I guess, aren't we? First, we call the function and save its result to variable got, so we can compare it with the expected result. What is the expected result, though, since we don't know in advance what S is? Well, we can't predict it, but we can ask the oracle that function from the standard library. This function will give us the right answer, and we'll store it in the want variable. Now we know that the fuzzer is going to generate lots of random strings for us to use as input, but are all possible strings actually valid? No, because not all strings encode valid UTF-8 runes. For example, the empty string doesn't. And there are many sequences of arbitrary bytes that don't happen to be valid UTF-8 data. So we need to do a little pre-filtering on our input before checking whether first rune actually handled it correctly. Makes sense. Suppose the fuzzer calls our fuzz target with some string that doesn't contain valid runes. What will our oracle function decode rune in string return in this case? The answer is the constant UTF-8.runeError. If we get that result, then this particular input value is invalid and we should just skip it. That's what the call to t.skip does. I see a quick win for optimization here, by the way. Does anybody else see it? We can move this got to after the skip is called. That way we don't end up calling our function needlessly in the case that is an invalid string. Not a big deal probably, but if you're running this millions of times, it might make an impact. You could probably get more fuzz testing done in the same amount of time. All right. A skipped test neither fails nor succeeds. The fuzzer just ignores it and moves on to the next randomly generated input. Why don't we skip the test? Oh, maybe he has a reason not to do that here, huh? Why don't we skip the test before calling first rune with the input? Because even though we don't require first rune to give the right answer, we do require that it doesn't panic. Okay, so there's, if we think the function could panic, that would be a reason to go ahead and call it. So he has a reason. He thought of this and chose not to do it that way. So that makes sense. If any fuzz input makes first rune panic, we want to find that out before we skip. Fair enough. Finally, just like in any test, we compare want and got and fail the test if they're not equal. The failure message is a little more complicated than we've written so far. Yeah, that looks like gibberish, doesn't it? Let's break it down. In the event of a failure, we want information. In the event of a failure, what information would we like to print? Certainly the input string that caused the failure, so that's the first piece of data. Yeah, this is the %q in a format string in Go. It's like %s, but it's quoted. So it not only has quote marks around it, but it escapes any characters that need to be escaped, like quote marks, for example. Even though this string is guaranteed to be valid UTF-8, we can't guarantee that all its characters will be printable or have a corresponding glyph in the display font we're using. Right. So just in case the string contains some non-printing runes, we'd also like to print its raw bytes as numbers. How can we do that? As you probably know, the fnt verb %x will print a piece of data as a hexadecimal value, and we can give the reader a clue that what follows is hex by prefixing the 0x. Fair enough. So a format string like this would do the job. Given, quoted string, and then the hexadecimal. Yep. For example, if S were the string hello and the test failed, this would print. Okay. But notice how we have to supply the argument S twice, which seems wasteful. As you know, every %verb in the format string has to correspond to a piece of data supplied as a subsequent argument to t.errorf. So if there are two verbs, %q and %x, then we need data arguments. We need two data arguments, even though we're actually using the same value. Is there a way to avoid this? Yes, there is. That's what the brackets and the square brackets and the number do. We can use what's called explicit argument index, which is a number in square brackets. This is kind of a side journey into how FMT, printf, and related functions work, but it's useful data, useful to know. This is interpreted by the formatting machinery as meaning print the nth data value. In this case, that would be number 1, the first data value, which is S. So that's why we have this square bracket 1, blah, 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 repeated. Notice that the square bracket is not needed for the first instance, since that is number 1. I don't know if we had a second argument. I don't know if we could omit the square bracket for the first occurrence of the second one, or we'd have to do square bracket 2. I don't know that. I'd have to play with it to learn. In the fuzzing example, we need to use S twice, once to print it as a quoted string and again as a hex value. So here's what we do. So far, so good. What about the next part? What was the next part? I don't even remember. Since both want and got in this case are characters, we'll need to use the verb %c to display them. And again, we'll use the explicit argument index, in this case 2, to reuse the same data, but this time printing it as a hex value. Okay, so then we say want %c, and then we repeat that. So apparently, you don't have to put % or the square bracket 2 for the first occurrence of the second value. That's kind of cool. Here's what that would look like if the test failed. Want W0x77. The final part of the failure message prints got in the same way. Good enough? That was a lengthy detour, or at least one that was a lot of words to say. So we're ready to write a null implementation of first rune and try out our test. All right, so I'm going to copy this test into my code. Blah, blah, blah. And now it's failing. I'm not going to do the runes package. I'm going to copy the empty thingy, the empty function, into the same package. Here it is. All right. This is definitely wrong, so let's see if the test agrees. Let's do it. Actually, I'm going to remove my old test data first. All right. Gathering baseline coverage, 0 of 2 completed. Failure while testing seed corpus entry. So even our first seed corpus entry failed, which would have been the add hello. And we see the same thing here. That's encouraging. So let's see what our carefully constructed failure message actually reports. Given we're world, blah, 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 want W got empty. All right. So the failing input is world, which was one of the cases we manually added to the corpus. What caused the failure then? The Oracle thinks the first rune of world is W, and I agree. But what first rune actually returned in this case was the rune 0, or was the rune value 0, hex 0, which corresponds to a non-printing character. This is exactly what we expect to happen since we deliberately wrote first rune so that it always returns 0 no matter what. Great. Now we know that the test can detect this bug where the function does nothing. That's a good start. In part 4, we'll fix the baby. We'll fix that bug by writing a real implementation of first rune. But we'll also introduce a new, more subtle bug. Ooh. I think this is where it gets interesting. This is the final article. In the earlier parts, I think we already covered that. Just skip past that bit. As usual, when developing a program guided by tests, we wrote a cheerfully rubbish implementation of first rune that does basically nothing, just to validate that our test is useful. If the test didn't fail with this function, we might start to worry a bit about whether or not it would detect any bugs. But it does indeed report reassuringly, and there's the same failure we saw. In other words, asking for the first rune in this string world gives us the rune value 0, which is incorrect. It should be W. Now that we've validated our bug detector, we can go ahead and write a slightly more plausible version of first rune, though as we'll see, there is still a problem lurking. All right. Yeah, that looks more plausible, and I can already predict the failure, but let's give it a try. We use the square bracket slice index notation, S square bracket 0, close square bracket, to extract the first byte of S, and we return it having converted explicitly to the rune type. If anybody needs me to explain that, let me know, but I don't think it should be too, even if it doesn't make perfect sense, I don't think it's really that important for understanding the fuzz testing aspect. Though plausible, this is still incorrect, and you can see why, can't you? This is the kind of code that someone might write, for example, if they didn't know about the distinction between bytes and runes that we talked about in part 3. It might even work some of the time, but only by accident and only when our input strings don't contain any multi-byte runes. Or more precisely, when our input string's first character is not a multi-byte rune. Let's see how far this gets. All right, run the fuzz test again. And it fails. Of course it fails. And it created a failure for us here. It seems that the 2 seed corpus examples have now been successfully checked. 2 of 2 complete. Do we have the same? Yes, 2 of 2 complete. And the fuzzer announces now fuzzing with 8 workers, meaning that all 8 CPU cores are concurrently generating inputs for the fuzz target. Do I have the same? I have 16 workers. Hoo-hoo. The more cores we have available, the more fuzzing we can do in parallel, of course. When we're reporting a bug we found manually, it's always worth taking a little time to find the minimum or the minimal input that still reproduces the bug. This will help maintainers because they can ignore the irrelevant parts of the input and focus on the parts that trigger the problem. By this shrinking process, we eliminate any part of the input that doesn't affect the outcome. The fuzzer does the same thing. If it finds some input that fails the test, it tries smaller and smaller versions of it, looking for the minimal failing input. Okay. Here it says minimizing 27-byte failing input file. Do I have the same thing here? I don't, because I think I got a different failure. You see, I got a index out of range failure. Well, that means it must have passed an empty string. Let's see if that's true. Yep, it passed the empty string. That's a different bug than the one his found randomly, which is kind of cool that by doing random testing, we get different random failures. Now I have to decide how to continue. Here's how I'm going to continue. I'm going to delete this. And rerun it and hopefully get the same failure he did. No, I got that one again. Try a couple more times. All right, so I'm thinking, well, it's not happening the same. So like this is after 35 executions, you see. So it had apparently 34 successful runs before it crashed, and this time it had 114 successful runs before it crashed. So it's not doing this deterministically at all. There we go. Now we got the same failure that he did. 55 byte failing input, minimizing it, whatever that means. I mean, we know what that means because we just read about it, but however, it's still... maybe this is the same thing that he got. Okay, it is. So I just, yeah, I don't know if I looked past that before or what, but he does have the index out of range happening also. So let's continue reading here. In this example, we can see that it found a 27-byte input string that caused the fuzz target to fail, or in my case, it's 55 bytes. It then tries smaller and smaller versions of the input to see if they still fail. This process continues until it has found the minimal input that causes the fuzz target to fail. And here it is. It seems that in this case, the fuzzer managed to shrink the failing input to completely the empty string. This is rather puzzling. What's gone on here? In fact, what's probably happening is that the fuzzer generated a random 27-byte string whose first rune was a multi-byte, causing the function to return the wrong answer. As the fuzzer tried to shorter and shorter version of the string, this same wrong result failure kept happening. Finally, when it reduced the string to length 0, it got a different failure, an index out of range panic, so it happens the first rune doesn't cope well with empty input strings. Yeah. As I'm sure you spotted right away, the slice index expression S0 will panic when S is empty, and indeed that's what we're seeing. Let's fix it. Indeed. All right. It seems reasonable to follow the example set by the standard library, which returns UTF-8 rune error in this case. Now the function won't panic when given an empty input. As you'll recall from our earlier example, when the fuzzer finds a failing input, it automatically saves it to the test data folder. This becomes part of the corpus. And even when we run test, yeah. So now if we're going to go test, it should pass. And if we use -v, we'll see that it's running that particular example. It is. Great. Okay, again, XXX is actually much longer, blah, 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 blah. The result of that is neither pass nor fail, but skip. Why? What? Okay, I wasn't expecting that. Oh, yeah, I think I know why. Remember when we first wrote the test, we said that we'll skip inputs for which decode rune in string returns rune error. That's true for the empty string, which is why this this case shows us as skipped. I don't know if he's going to leave it at that, or if we want to change that to not skip in that case, but we'll leave it for that as that for now. The fuzzer has already proved its worth by detecting a panic in the first rune function when it's called with the empty string as input. But are there still more bugs? Yes, there are. In the previous example, we saw that the fuzzer found a 27-byte string that caused a test failure. That can't be due to slice overrun bugs, so there still must be some other bug remaining. So I'll run the fuzz tester thingy again. And there we go. All right, so now his is going to be different than mine because randomness. But in my case, it looks like I don't know how many we ran, but we very quickly apparently found a 29 byte failing input file, and we got given this. We want this, but we got this. It looks like an O, but I don't think it is. It's definitely more than 1 byte. It's got 3 bytes in it, so it's not a regular O for sure. Again, interpreting the output, we can see that the fuzzer found a 32-byte failing input, or in my case it was 29 bytes, which it then managed to shrink to just 2 bytes. Yeah, mine was shrunk to 3 bytes. His was 2 bytes. That is, the input string consists of the rune whatever, which in UTF-8 is encoded as 2 bytes, blah, blah. If first rune had correctly decoded the string, it would have returned the same rune, the same result as the oracle. Instead, it mistakenly interpreted the first byte of the string, blah, as a single byte rune, in this case the letter E with a little hat. A victory for fuzzing, even if we didn't know about the distinction between runes and bytes in Go, and even if we might not have thought of using a string like blah 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 as an example input, we were still able to find the bug. So fuzz testing is very useful in situations where there's a wide range of possible inputs and where the function may return correct results for some inputs but not others. This is usually true whenever the system accepts user input, for example. Users input all kinds of crazy things that our system, even though they shouldn't do that. So any program that needs to parse or transform user input or arbitrary data of any kind is a good candidate for fuzz testing. Even when we can't check the exact results of a function in a fuzz test, we can still catch panics and hangs, or timeouts. And we may also be able to test some properties of the result, as with the square example we saw. What to do with fuzz-generated test cases? As we've seen, the aim of fuzz testing is to generate new failing test cases. So what should we do with results? It's not generally a good idea, for fairly obvious reasons, to derive passing test cases from the current behavior of the system. That would start by assuming that the system is already correct, which doesn't help us much if that's what we want to prove. But it's absolutely a good idea to do the opposite, to automatically create test cases that cause this current system to fail. This goes back to what I was saying on a live stream 3 weeks ago, I think, that when tests fail is when they provide value. So he's kind of restating the same thing. If a test always passes, then it's not giving it's not giving you any feedback, right? You want feedback from tests, which means they have to fail sometimes. Which is why if you're doing test first coding, you write your test first, prove that it can fail before you write the code to make it pass. That way you get your feedback before you even write your code. A false positive bug detection, that is, a test failure that doesn't correspond to a real bug, is much less serious than a false negative, where there is a bug but you don't know about it. Because fuzzing can create new test data, you'll need to remember to check those changes into your version control system. That's why it really only makes sense to run the fuzzer manually, for example, on your development machine, rather than automatically. In a CI pipeline or GitHub action, the CI system would have to be set up to detect any changes and commit them to version control, and that's usually not straightforward. Fuzzing can take a while too, so we wouldn't want to do it every time we run the test. A good time to try fuzzing is when you think you've covered the system pretty well with example-based testing, but you suspect there may still be bugs lurking. The more critical the reliability and correctness of the system, the more fuzz testing you'll want to do. The examples we've tested in this series have all resulted in failing cases being found fairly quickly. But what if it doesn't happen? How long will the fuzzer keep trying before deciding there are no failures to be found? The answer is that it will keep trying forever. A test run in fuzz mode, if no failures are found, will never terminate. And that makes sense. It's unlikely that we would ever completely exhaust the space of possible inputs. Well, that depends on what the inputs are, right? I mean, if it's a uint 8, then there's 256 possible inputs, and I think it would exhaust those pretty quickly. There are always more bugs to be found. You'll probably find that on your first few fuzz runs, there are plenty of failures to keep you occupied. Once you've found and fixed the bugs responsible, the fuzzer may run for a while without any results, perhaps several minutes. If you like, you can leave it running for several hours or even overnight. You never know. It might find something. Once you decide there's not much more to be gained by further fuzzing, though, or if your CPUs are starting to melt, you can terminate the test run by typing Control-C in the terminal. Alternatively, you can run the fuzzer for a fixed time period using the fuzz time flag, for example. How should we implement first rune correctly then? Well, that's not really important for the discussion of fuzz testing, but I don't want to leave anyone in suspense. Let's see if we can fix this bug. Well, the short answer is to just use the standard library, right? But that's not the point. There are a variety of ways you could fix first rune correctly, including the rather dull one of simply calling, that's what I just suggested, calling the standard library. But here's a slightly more interesting version of it just for fun. Okay, yeah, by ranging over S, you get the runes rather than the bytes. Let's go ahead and implement that. Let's see our tests pass. Now tests are passing, except that one that's skipping. So the empty string one still is skipped, which I don't really like. In fact, I'm going to fix that. It's not part of the tutorial, but I'm going to fix that. I'm going to change this to if want equals this, and got does not equal that. So I don't want that one to skip. There, now they're both passing. All right, let's run the fuzzer again now and see what happens. Found some interesting ones. I'm curious what's interesting about them. Meanwhile, let's continue reading here. Why does this work? As you probably know, the range operator iterates over strings by runes, not by bytes. That's something I have known, but it's not something that's how do I say? It's not something that's top of mind. I don't remember that as a regular thing. When I saw it here, I was like, oh yeah, that must be what's happening. But that's not a characteristic of the range function on a string that I know by heart. But it makes sense. But on the very first iteration, we hit the return statement inside the loop body, and we return the first rune straight away. After all, that's the right answer. In this case, where S is empty, the for loop will execute 0 times. That is to say, not at all. We'll go straight to the end of the function and return the value 0. I think this is correct, but let's see if the fuzzer agrees, or rather, we'll give the fuzzer a chance to find some counterexamples. All right, he found well, let's see. In fact, I let this run for a minute or two, but it didn't find any more failing inputs. That doesn't guarantee there aren't any, of course. I'm really curious what this new interesting means. Added new baseline cover. So this is, I have to look this up unless he gets there. So we started with 0 of 5. So we added 2, and we had 2 failures that were stored. So there's another one somewhere. And then found 6 new interesting ones. I don't know what that means. And now we're starting with 11. So it stored those interesting things, whatever that means, somewhere. I guess. Let's keep going and see where it goes. If it doesn't answer these questions in my mind, I'm going to look it up. Yeah, here we go. One interesting thing you might have noticed about this output is the word interesting. What does that mean? It turns out that the fuzzer does more than just generate random inputs. It also looks at which code paths are executed by the inputs. Okay. It considers an input interesting if it causes a new code path to be executed at the system under test. After all, if there's a code path that's executed by no other test case, bugs could definitely be lurking there. So the fuzzer tries to discover inputs that cause new code paths to be executed. If it finds any, it uses them as a basis to generate similar inputs, hoping to find one that triggers a failure. Nice. A question might occur to you A question that might occur to you is how the fuzzer knows which code paths in your system are executed by any given test case. The answer is that it uses the same runtime instrumentation with which Go calculates your test coverage. That makes sense. And if you'd like to know more about that, go straight to the Happy Fun Bookstore, blah, 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 and buy his book. By the way, he has great books. I did a review of one of his books, For the Love of Go. It's really designed for beginners. If you're new to Go or don't know Go at all yet, it's an excellent book for you to read. It's available in PDF format. It's not a print book that I know of, but it's a really easy book to read. It's fun, so I highly recommend it. Thanks for reading this series, and if you'd like to be notified every time I publish new Go material, be sure to join the Go Club by entering an email address at the bottom of this page. I'm already a member, so I'm not going to do that, but you're all, of course, welcome to join his mailing list. Still don't know where that stores that interesting stuff, but anyway, we made it through. Are there any questions? We've been going a little bit more than an hour. I scheduled 2 hours today. I might try to think of a project where I can do some real life fuzz testing to play with this a little bit. I'm not sure what project that would be. I'll think about it here for a minute. Let's see. I have too much crap in this folder. Oh, I know. Yeah, fuzzing would be great here. I have a library I wrote that converts HTML into text, and I use it to post on LinkedIn. So I told you I have a daily mailing list where I write about Go. I have another daily mailing list where I don't write about Go, and I automatically post that one to LinkedIn. And so it converts. So I use this library to convert HTML into a LinkedIn post, essentially. Let's try adding some fuzz testing here. I'm really curious how fuzz testing works with HTML inputs. So I already have a test file here that doesn't do any fuzz testing. You see it just regular tests that I've done. Testing the case where it converts bold into this, and where it converts a div into just removing the div, basically. Let's try doing a fuzz test here. Come to the bottom. Oh, there's fun ones where it converts into tables. All right, let's look at the tutorial, and we're going to copy, or we're going to look at it for guidance on how to create our fuzz test, because I don't remember it. Here we go. Func, fuzz, and what am I fuzzing? What's the function that enters here? The enter function. Do a split screen here. Put my tests on my right, and my live code on the left is the way I like to do it. It's a little bit crowded on this small screen, but when I'm usually coding for myself, it's a bigger screen, and I don't zoom in quite so much. I zoom in for the live stream to make it easier for you all to read, especially if you're on your phone or something like that. I should just look at one of these other tests, what it does, how it calls. Does from string. Let's try that. No, that's not. That's probably what I want, but that's not this particular test I want to be copying. I don't remember what all this stuff does here. Want string. What does that even do? Oh, it just does a check for me. Okay. Let me look at the public API I've created here and try to use that instead. I think from string is what I want. Seems like an easy way to start. So let's do from string, and then f testing.f, and So I don't know how I'm going to test. I'm not sure how I'm going to do this actually, because I have no idea what the output is going to be in any given case. I can test that it doesn't give an error, but that's not going to be useful because almost all inputs will have some sort of parsing error. All right, I'm not actually sure how useful this is going to be. I might need to think of a better thing to test. Hmm. Maybe I'll just try it and see where we get. And I can at least check that it doesn't panic, although I don't think any of this code panics anyway. Hmm. Well, let's just see what happens. I don't think it's going to be useful, but we're going to try. I'm just going to check for error to start with, right? Let's just add a really simple input. I don't think this is going to be useful at all, but let's see. First, make sure that tests pass. The tests don't even pass. What's wrong with my code? How do I have failing tests? I don't even understand that. It's hard to. I mean, it looks like I have a bunch of debugging code here. So I don't know the status of this even thing here. So the question is, what would fuzz testing be useful for? I'm trying to figure that out here. I mean, I conceptually have some ideas. I was thinking it would be useful here to ensure that I handle uh, unusual, HTML inputs and convert them properly. But I need to know what they should be converted to before that's useful. So I don't know if it's useful in this case. But I mean, it could be useful anytime you have uh, unexpected or uncontrolled inputs that you want to validate in some way. The tricky part that I'm struggling with right now is how can I validate it? Like in this case, if I want to convert HTML to text, I need to know what the text should look like, or else how do I validate that? I could maybe do some property-based testing, like maybe there's some properties of the output text that I can check for, but I can't think of that right. I can't think of what that would be right now. So I'm not actually sure what that should be. I'm gonna look for a different place to do this because that library it's not even working right now, and I don't know why. I don't want to debug that right now. Let's see if I can find something else that might make sense to play with. I have a database library that I probably want to use fuzz testing for eventually, but I need to think about that for a while. Maybe this will be next week's live stream, is adding fuzz test to a real project where it might actually be useful. I mean, so it could come through in normal testing if you know to test that test case. But fuzzing will help you find the cases to test if you're not sure, or if you don't think of the test cases. Like it found, for example, during the tutorial, it found the index out of bounds error, which would be a really easy thing to forget in your own test. But by doing fuzz testing, it will catch that sort of thing for you. And that's the kind of thing that even for my HTML converter, it might detect bugs like that if I just pass it arbitrary stuff and I test that it doesn't panic. But since it's not even passing right now, the standard test, that's not really very useful. I think I need to spend some time on that library and clean it up before I do that. What else could I try? Well, you know what? I think I was in the wrong branch. Or in the wrong repo even. Yeah, let's try it here. Yeah, that one I was playing with was an early attempt. I should delete that one. But this is what I actually want. So let's try this again. Func fuzz render plain text f testing.f. And then what do I call the inner function? f.fuzz func t testing.t. And then my input, I suppose, would be a string. And then how do I call this thing? So the main thing I want to check for here is that nothing panics. So I don't really care about. Okay, so what I'm going to do is I'm going to take a random input and pass it to HTML parse, which is part of the standard library. And if that gets an error, I don't want to fail. I just want to skip. And then I'm going to pass that to my renderer, which is this. Don't need to give me options. And if that fails, I'm not sure what would cause that to fail. So I think that's what I want right there. Oh yeah, that should not fail. That's just generating the renderer. And then here, so that should not fail. So fatal would be fine. In fact, I should just call this once before the fuzz testing starts, because that's. Let's call this panic. No, I won't. I'll leave it as it is for now, at least. So here is where if I get a failure here, then I want to report that. Let's see what happens. First tests are passing good. Waiting. Waiting. Yeah, so I don't know exactly how this library would handle blank HTML tags, or if there's a missing closing tag. Those are the sorts of things that I would want to see happen here. So no panicking or crashing or errors at all yet, but it's finding a bunch of interesting things. I guess that's cool. So every time it finds a new interesting case, it's executing different bit of code. So that's kind of cool. I think it's fascinating that it's found 124 different ways through my 126 different ways through my code just by generating random text. I haven't even told it that it takes HTML input. I wonder if there's a way to see what those interesting cases are. That would be fascinating to me. I'm going to try to pull it up in another tab. I don't know where those interesting cases are stored. I'm going to stop this right now because it's slowing my system down, running all 16 cores simultaneously. And I'm going to look this up. Go fuzz testing. Where are interesting cases stored? The generated corpus during fuzz execution. It's stored in a global cache, so it's not part of the. It's not stored in the repo, but maybe I can see where. Look at that. Okay, so I can see the examples here. Let's just look at one. Okay, so it's the string 0 bracket exclamation backslash x. That kind of looks like vaguely HTML-ish stuff. Another one or two. Ampersand 00000. Ampersand sign. So the ampersands are probably interesting because they trigger different because they represent HTML escape sequences. 0 space 0. These are funny. Yeah, it doesn't expose which of the which code is executed is what you mean, right? By the way, welcome, John. John is here. Bitfield Consulting is on YouTube. He's the one who wrote the blog post, so welcome. I'm glad to have you here. So I'm going to add some of my own here. I'm going to run the fuzz again. Ooh, we got a panic. Fuzz testing for the win. All right, so we had a failure in render heading. Let's have a look. Make this a little bit bigger here. Render heading line 341. So this line here failed. So I think that failed because this is not part of an HTML body tag. So it's assuming, I think. I'll have to debug this a little bit more. Yeah, that's cool. I find a panic here. So I was a little bit skeptical that this would be very useful without the ability to validate the outputs. But finding a panic is definitely a useful thing. So that's cool. It must be trying to dereference this. So n must be nil for some reason. I don't know how that's possible. So I can just run go test and it will fail. That's great. So I can just test this and do some debugging here. By the way, I want to see what that test data looks like. Test data. Oh, it's just the string h1 with nothing. So if h1 is missing a closing tag, apparently it causes this. That must be the case. Huh. Oh, because it has no child. Oh, it's an h1 tag with no child. So that's why this is failing. So that makes sense. So how would I want to handle that? I think I just want to early return in that case. If in dot first child equals nil, return nil. That might solve it. That fixes the panic. All right. One bug down. See what else we can find. This makes for some riveting TV, doesn't it? Hey, another panic. This time when rendering a bullet. Let's see what the input looks like. It's pretty cool that that this found that that creating an li tag is a thing. Let's see what's going on here. This is line 82. Ah, I know why this is happening, and it's due to some internal details of the way this code works. But since there's no, this is an li tag without a ul or an ol tag surrounding it, it hasn't set up the context internally to handle it, and that's why this panic is happening. So I would definitely classify that as a bug. It's a bug that I probably knew about when I wrote this code and decided I didn't care about it at the time. So it's something I should fix. I probably won't fix it on this call. Excuse me. I won't fix it on this live stream. Yeah, to misquote RFC 1122. In general, it is best to assume that the network is filled with malevolent entities that will send in HTML design to have the worst possible effect. If this library was meant for general use, I would definitely agree with that. the fact that I wrote this library for personal use only, just to publish my personal blog to LinkedIn. I generally assume I'm not being malicious to myself, uh, but I still like to fix this bug. I mean, there's no reason I shouldn't make this library useful for others if I can get it working. So I think I'm going to wrap up for today. Unless there's questions, I mean, I'm happy to. I have another 25 minutes set aside to do this, but I don't want to just be breathing into my microphone. But if anybody has any questions about fuzzing or anything related to Go at all, or my favorite flavor of ice cream or whatever, let me know in chat. I'd be happy to use this 25 minutes for the benefit of anybody here if there's something I can do in that regard. If I don't get a question in the next couple of minutes or so, I will end this call. Well, I hope you'll come back next week. I'll be doing another live stream. I'm trying to do this every week at the same time for 2 hours. I don't know what I'll be streaming about next week. Maybe I'll do some more fuzzing. Maybe I will work on a different project. I don't know, but I'll do something. If you have a question that you'd like me to answer live, that's a great topic starter too. Have you ever considered doing online code videos to show how a senior dev works in Go? Well, that's one of the things I've done a few times on this live stream. So the last few weeks I was writing a linter, and those live streams are on YouTube, by the way. If you want to go watch those, you want to catch the replay. I have six of them, I think, and but yeah, that's definitely something I could do. I mean, so I have an open source project. I could work on this library, this HTML library, or I might work on my database library I mentioned earlier next week, and just do some coding along those lines. Oh yeah, mentioning that there was some interesting stuff I did with the Go docs. Yeah, I do that all the time when I see a new function that I'm not familiar with. I pull up the Go docs online. So that's something I do. I think I do when I'm live streaming too. So maybe next week I'll just do some live coding on one of my projects to do that. John asks, could I briefly review my fuzz target, perhaps, and say how you might extend it? Yeah, I'd be happy to do that. I don't know how I'll extend it. I'll try to think of something though. So at the moment, it's just I'll explain what these different steps do. So this step parses the input string as an HTML document using, is it the standard library? It's not technically the standard library. It's golang.org/x/net/html. It's like the standard library junior or something. It's written by the Go team, but it's not considered part of the standard library, so it doesn't have the same backward compatibility guarantees, but it's standard. So it parses that into an AST of HTML nodes. That in turn gets passed into my renderer here. This step here just instantiates the renderer. I can pass in optional arguments here, which I'm not doing right now. So that's one place I could extend this. I don't know if it would make sense to fuzz those options. I think they're pretty limited. It takes functional arguments here. Yeah, I don't think you can. I don't think you probably fuzz that. I don't know. It lets you specify like how bullets are styled and stuff like that. Is what that's for. And then here, so this is where the actual textual output of the HTML to text rendering is output. Obviously, I'm ignoring that now. It might make sense to do some sort of property-based testing on that. Make sure it ends in a new line. Make sure, I don't know, I would have to think about that a little bit. What sort of general characteristics I could test on that. But the fact that I found 2 panics already just by doing this is quite encouraging. I'll bet I could find a lot more. So I probably would just run with it as it is for a while. I might add some more preceded corpus tests, whatever that's called, here to give it some, with tables and maybe some of the more archaic HTML tags that aren't used very frequently. There's lots of them. Forms, nav, divs and spans, and all sorts of all sorts of stuff. I might put some of those in here and to help give the fuzzers some inspiration to how to break things. Just adding that H1 gave it my first panic, right? Apparently it randomized that and ended up chopping off everything except H1, which led to a panic, which was a clear bug. So it looks like there's plenty of room for this to find bugs as it is. I would probably run this. I probably will run this actually in the background, maybe while I'm working on other things, or maybe not, since it's using my CPUs. Maybe I can have it use one core only or something, so it's doing stuff but not slowing down my workload so much. Yeah, I hopefully by running this exact fuzz target for a while and fixing some bugs, I'll get some inspiration on how to do others. I have a sense. I'd love to hear from you, John, if you can confirm or deny this. But I have a sense that fuzz testing is one of those things that once you get used to it, you start to see benefit, or you start to see use cases for it all over the place. And since it's still a new concept to me, as it was to Jason, who mentioned on chat, what would you do with this? I suspect that at first it can take a little while to start to see the use cases. But I imagine that once I start playing with it enough, I will find really useful uses for it. John mentions, if you could find another HTML rendering package, you could perhaps test the outputs against yours. I could. If I could find another HTML package, I wouldn't have written this one, though. Although maybe I could find one in a different language and render the, sort of, if I could find one in Python or something, that would probably make the fuzz tests really slow to execute a Python script and compare the output with Go's. To be clear, I did find some libraries to do this in Go, but they didn't have nearly the type of output I wanted. They just didn't work the way I needed them to. So that's why I did this. Yeah, I don't know. John says, I've found fuzzing especially useful for state machines because it can always imagine illegal states and inputs that I can't. Yeah, that makes sense to me. Yeah, all right. I don't know what else to suggest or to say here. I will be playing with fuzzing more. That's why I wanted to do this. I wanted to learn it. I was aware of its existence for a couple of years. I knew it was going to be in 1.18 before it was released. I've never played with it. Now I have, and I like it. Already found 2 bugs in this library, so I'll be playing with it more. And maybe that will be something else to come up on this live stream in the future. Any other comments or questions before we sign off? In the future, could you do something with the YAML provider in Go? What would you like me to do with the YAML provider? I mean, I've written some code that definitely uses YAML. Oh, it would attract a lot of DevOps people. Yeah, that might be true. So one of my projects, why don't I just pull that up here, that uses YAML. I can talk about that for a second here. One thing I was wondering about is how I could write YAML pipelines instead of using YAML. For that specific question, I might recommend Q. I think it's QLang. Is there a website? Q, CUE, Configuration Unity Executive, I guess is what it stands for, is a config file format of sorts that compiles to other languages like YAML or JSON or whatever you want. It's written in Go. I actually know I've met a couple of the main programmers on it. I'm not. It might be useful if you could help elaborate on what you mean by write YAML pipelines instead of using YAML. Oh, you hate YAML because of white space. Yeah, who doesn't? Q will help you solve that problem. Q will let you write your stuff in Q, and then it converts it to YAML before you push it to Kubernetes or wherever you're using it. So that Q might be exactly what you need if your goal is to not use YAML because it's ugly and error prone. Q might be what you want. I haven't used Q yet, but I would like to. It's one of those things that I would really enjoy doing at some point. I haven't been doing enough DevOpsy things in the last couple of years to justify learning Q yet. Back when I was managing Kubernetes clusters and so on, Q was top of mind as something I wanted to learn. I just never quite got there. So yeah, check out Q, qlang.org. I highly recommend looking at that. And let me know. Let me know if it solves your problem, Jason. I'd love to hear from you about that. Make a Go program to build a .NET app, but then output it as YAML so that I can put it in DevOps. Yeah, I think Q can kind of do that sort of thing for you. Check it out, and maybe it doesn't, but have a look at it. And they have a channel on the Gopher Slack. I think it's Q, or is it Qling? Let me just check. I'm not sure if I'm still on that channel. I was for a while. I thought they had a Slack here. Yeah, it's a small one, only 30 members, but that's their official channel. So you can, if you're on the Gopher Slack, join channel Q, and you can ask questions there. Yeah, check out Q and see if it's useful. And if not, let me know, and I'll try to come up with a better answer. All right, so yeah, thanks for everybody. Thanks everybody who's joined today and watched. Thanks for all the great questions in the chat. Look forward to seeing you here next week, hopefully. See you then. Now, if I can just figure out how to turn off this live stream, I'll be streaming forever.